So this is one of the most subtle problems that you'll come across in the course having to do with buoyancy and fluids. And this kind of problems cause a lot of problems for students in general. So what do we have here? We have three containers. They each have different amounts of water in them, but they have objects placed in them such that the water is all at the same level, right? So they're all filled to the same level. Oops, I accidentally moved everything. If we took one of these buckets and put on a scale, which one would weigh the most, which one would weigh the least? So the general tactic is to compare everything to a container that's just filled with water. So this is going to be our baseline. A was going to be our baseline. And what we're going to do is we're going to try to figure out if C weighs more or less than this container of water, and if B weighs more or less than this container of water. That's going to be our general strategy. So let's start with C, since that's the simplest. So what we notice is that if I look at the similar volume as this little object here, right? I've got this little rock at the bottom. If I look at the similar volume over here in this empty thing, I know that because this rock is sitting on the bottom of container C, that it must be a higher density than water. And because it's taking up the same amount of volume as this little bit of water, I know that container C must weigh more than A, right? So that's something I know. So I guess maybe I'll put it over here. Container C is greater than A. And I think that comes fairly straightforward. The second one is not very straightforward and is really subtle, and I think really tests your knowledge of buoyancy. So is B greater or less than the weight in A? Well, what we have to do is we have to figure out, well, how much does this block weigh? And how much water has been displaced? This really tests Archimedes' principle. What Archimedes' principle says is the buoyant force that is acting up, FB, is equal to the weight of displaced fluid, which is the fluid that's displaced by this object under the water. Well, the trick is to realize that, well, FB must be equal to mg, the mass of this block, right? So what does that mean when we look at it? Let's look at this balance. So we have FB, which is equal to rho water times g times the volume displaced is equal to the mass of the object times g. So the mass of the object is then equal to rho water times v displaced. It's equal to, like, the total mass of this object is equal to the mass of displaced water. And this is the key. What it means is that we could take this object out and replace it with this much water, and it would weigh the same. Well, how much water is that? Well, that's the water that's just under the surface here. So this whole container, if we took out the object and replaced it with this amount of water, it would actually just be equal to A, right? So this is the subtle point that we have to realize. And so our sort of long story short is that B actually weighs the same as A. And this is a really fundamental concept in buoyancy. And if you understand this, I think you get buoyancy.